Hello students, so this is our part 4 session in the chapter atoms, and just you recall the previous class. In previous class I would discussing about concept of Rutherford's atomic model, and then we studied one simple derivation regarding this electron orbits, and before that I have studied about alpha particle trajectory. So, and there I have given you regarding the information regarding impact parameter and all. So, with respect to the previous class, and now we shall go for next concept of this chapter atoms, that is atomic spectra. So, what is atomic spectra? See, each element has got certain characteristic spectrum. So, each element has got certain characteristic spectrum. So, what is the mean of this? What is the meaning of this? Say, if you consider certain elements in a gaseous state or in vapor state or in atomic state, and if you excite them, so how to excite? What do you mean by excitation? Means suppose if you illuminate some part of energy or by supplying electric current to that atomic gas or a vapor, then excitation of atoms will take place. And once if you analyze the light emitted by the excited atoms, once if you analyze the radiation emitted by the excited atoms while coming from higher energy state to lower energy state. Generally, when you incident energy or when you supply some amount of energy for the atomic gas or a vapor, the atoms in lower energy state, they get excited to the higher energy state, and they can't stay in the higher energy state for a longer time. Within a fraction of time, they will be elevated to the ground state, means they will come back to the ground state. So, during this condition, they emit certain particular frequency of radiation, and this type of spectrum we call as line emission spectrum. So, our topic is atomic spectrum. Atomic spectrum. So, under this atomic spectrum, generally spectrum means a band of colors, a set of frequency of colors, a set of particular wavelength of colors. We call them as a spectrum. See, we know that when white light passes through a prism, it will splits into 7 colors. We call that it is a spectrum. Band of colors is called spectrum. In the same way, when an atomic state of some particular elements or in a gaseous state of some elements, if I consider and if I excite them, if say this is the gaseous state or vapor state of some particular elements, you think, say suppose if it is in the atoms are in ground state, means they are associated with lower energy. Suppose if you pass an electric current or some amount of energy, if you pass on that atomic gas or a vapor under low pressure, so electric current, then what happens? They get excited to the higher energy state. They get excited to the what? Higher energy state. They get excited to the higher energy state. This is ground state. This is ground state. Is an excited state, you think. Excited state. Then after their excitation, they come back to the ground state by emitting the radiation. They emit radiation while coming from higher energy state to the lower energy state. So, this radiation which is emitted from the atomic gas or a vapor after the excitation is called line emission spectrum. This is called particularly line emission spectrum. Suppose if you analyze this spectrum, suppose if you analyze the line emission spectrum, so what it consisting? It consisting of some specific wavelengths, some particular specific wavelengths, and these wavelengths are in regular pattern. So it consisting of what? Some specific wavelengths of that particular radiation or that particular light. And remember, line emission spectrum consisting, and if you analyze it, the spectrum will be of what? It consisting of dark background. It consisting of a dark background. This what I am representing, it is a dark background. On this dark background, there will be some bright lines. We are observing some bright lines. So very bright lines we are going to observe on a dark background. Bright lines we are going to observe on a dark background. That will be the line emission spectrum. Say this is a dark background, you think. It's a dark background. On a dark background, we are going to observe that bright lines. Some bright lines. Okay, so bright lines these are. And this is dark background. Dark background it is. And we are going to observe a bright lines. These are the bright lines here. So this type of spectrum is referred as line emission spectrum. Then what is the use of this type of line emission spectrum in physics? Listen here. The study of line emission spectrum is a fingerprint for identifying the particular element in that gaseous state. So it will help us to identify the element present in the gaseous state. This is called a spectroscopy. If you go to the higher branch, if you go to the higher level for higher studies in physics, you will be going to study in detail about the spectroscopy and detailed study of spectrum. At the time, you are going to get that idea regarding the spectrums and the idea regarding the line emission spectrum in detail. So here, what is the use of this type of excitation of some atomic state? So this is nothing but a gaseous state, you can think, a gaseous state of an atom, gaseous state of atom, or it is a vapor state, okay, vapor state. When it is subjected for excitation by supplying some energy or by passing electric current under low pressure condition, then what happens? The excited atoms will re-emit the energy, and that energy will be consisting some bright lines on a dark background. This is completely dark background. On that we are going to observe a bright lines, and that is nothing but the what? A line emission spectrum. The use of this type of spectrum is to identify the element present in the gaseous state. And next is, this is a one type of spectrum, that is a line emission spectrum. We have another one type of spectrum, that is line absorption spectrum. So what is line absorption spectrum means? Say when you allow a continuous range of wavelengths, a continuous range of wavelengths. So generally continuous range of wavelength we can obtain with the help of incandescent source of bulb. That incandescent source of light can be obtained with the help of that very simple bulb. So it will gives out the light consisting of continuous range of wavelength. Suppose if you incident such continuous range of wavelength, suppose if you incident such a continuous range of wavelengths, okay, see it is a bulb here, it emits continuous range of wavelengths. It emits continuous range of wavelengths. Suppose if you incident continuous range of wavelength of light, generally wavelength of light it emits. When you incident such continuous range of wavelengths on an atomic gas or a vapor, of some particular element, gaseous state of atom, say vapor state of atom, vapor state of some atoms of some particular element, then what happens? The atoms are going to absorb their energy. Atoms will absorb some part of the energy of this continuous range of wavelength, and the transmitted light, see here, transmitted light I am going to observe now. The light which get after the absorption by this vapor state of an atom, so transmitted light I am observing. Transmitted light I am observing. So when I subject the transmitted light for the study, I am going to observe that there is a bright background. There is a bright background on which I am observing a what? Dark lines. And remember, the whatever the vapor state of atom I have considered for the previous one while explaining line emission spectrum, the same I have considered here, but instead of supplying current, I am supplying some continuous range of wavelengths. Then I am going to observe that. The transmitted light for the study, then I am going to observe that the bright background, means transmitted light consisting of a bright background is there. The background is very bright. So on a bright background, say bright background, there is a bright background. On this bright background, I am observing a dark lines. I am observing some dark lines. And these dark lines are corresponding their wavelength in case of line emission spectrum. So whatever the wavelength corresponding to the line emission spectrum emitted by this atomic gas or a vapor, these wavelengths are missed here. And where is these wavelength? They get absorbed during their excitation, and once again they give out in case of line emission spectrum. Suppose if you study transmitted light after the excitation, if you study transmitted light, some wavelengths are missing here, some particular wavelength of radiations or light is missing here, and this is corresponding to the what? The previous wavelengths which are present in line emission spectrum, and this spectrum is called line absorption spectrum. This is called line absorption spectrum. So this is very important topic here. This is called line absorption spectrum. Okay, so what is line emission spectrum? When an atomic gas or a vapor state of some particular element is subjected for excitation, and if emitted radiation is analyzed, then it consisting bright lines on a dark background. Such type of spectrum is called line emission spectrum. And the second one is line absorption spectrum. Suppose if a source of light from the incandescent bulb, it consisting continuous range of wavelength, if it is made to incident on a atomic state or gaseous state of some particular atom, then if you observe the transmitted light, if you analyze the transmitted light, so at the time you are going to observe that the dark lines on a bright background, and this corresponds to the what? Line absorption spectrum. So this is the concept atomic spectrum. So next concept is spectral series. Next concept is spectral series. So you have heard about arithmetic progression, geometrical progression. So you have heard about AP series, GP series, like that. So there will be some order, no? In case of AP or in case of GP, there is some particular order will be there. Is it right? So there is some regular arrangement will be there in the numbers pattern. In the same way, here why we called as a spectral series, the word why we have given that suffix as series for spectra there. Here also, if you study the line emission or line absorption spectrum, there will be some proper order arrangement. There is some regular wavelengths are present. So that is the reason it is called as spectral series. So what is spectral series means? If the frequency of the radiation emitted by a certain particular element, if you analyze it, it consisting some regular patterns. It consisting some regular pattern, and the spacing between those regular pattern also, that is a decreases with certain sets. Okay, say suppose if I say a definition, so if I put the figure very simple, you can understand it. So let us consider this is a simple spectrum of hydrogen atom. See, this is the thing. It is nothing but the spectrum of hydrogen atom. Better I would like to give this completely. So spectral series, so simple spectrum of hydrogen atom, that is a line emission spectrum. It is line emission spectrum of the simplest atom if you take, that is a hydrogen atom, spectrum of hydrogen atom. So I am going to draw here that, just you can. Delta See, what is a spectral series? What is spectrum of hydrogen atom I am representing here, and this spectrum of hydrogen atom we are observing in visible region. Later on I will tell. What is spectral series? If the frequency of the radiation emitted by a particular element, if you study it, then it consisting of some spectral lines, and these spectral lines are arranged in a regular pattern, and the spacing between these spectral lines will be decreases with a decrease in wavelength. With a decrease in wavelength, the spacing between the sets of line also decreases, and we call this as spectral series. So what is spectral series? The frequency of radiation emitted by a particular element exhibits some regular pattern. So frequency of the radiation emitted by a particular element means, so we can also express that in terms of wavelength also. So frequency of the radiation emitted by a particular element exhibits some regular patterns. So this is the regular pattern of one part of hydrogen atom it is. So hydrogen will be, has got its spectrum in three regions. So in visible region, as well as in infrared region, as well as in the microwave region also. So it has got in three regions, it exhibits its ultraviolet region, visible region, as well as in infrared region. Sorry, not microwave, in infrared region. So it exhibits its spectrum corresponding to the wavelengths of infrared, visible, as well as this ultraviolet. So among that, I have taken one simple part of the one series of hydrogen atom it is. So that is spectrum of hydrogen atom. So what is spectral series means? Spectral series is nothing but the what? The frequency of the radiation emitted by a particular element exhibits some regular pattern, and these regular patterns are decreases with certain sets. Then these sets of lines are called as spectral series. It is called as spectral series. Let us consider a simplest atom, that is hydrogen atom. Let us consider a simplest atom, that is hydrogen atom. Suppose if you analyze the spectrum emitted by hydrogen atom as particularly in a visible region, if you observe one of the spectrum, I told you hydrogen will emit its spectrum not only in visible, even in ultraviolet as well as in infrared region, but I am taking only visible part of hydrogen spectrum. So let us consider a simplest atom, that is hydrogen atom, in its visible region. When you analyze the visible part of the hydrogen spectrum, then it consisting of 4 spectral lines. We call them namely as H alpha, H beta, H gamma, as well as H delta. And remember here, H alpha consisting of wavelength 6563 angstrom. And this H alpha spectral line is observed in the visible region, and as particularly in visible means at what region we are going to observe. So here H alpha corresponding to the wavelength 6563 angstrom, H beta corresponds to 4861 angstrom, and this H gamma consisting of 4341 angstrom, and this H delta is 4102 angstrom. So here H alpha is called as the first line of the hydrogen spectrum in visible region, and particularly hydrogen spectrum in visible region was studied by the person Balmer. Hence we call this as a Balmer series. It was studied by the person Balmer, John Jacob Balmer, and hence it is called as Balmer series. We call it as a Balmer series here. Indirectly this spectral series of hydrogen atom is called as Balmer series, and this Balmer series consisting of H alpha line in the red region. So we are going to observe this corresponding to red region of visible spectrum, and this you are going to observe in the blue green. Between blue and green you are observing this H beta line, and this H gamma you are observing in the region of blue part of the spectrum, whereas H delta you are observing in the region of violet. So this H delta, this is H gamma, H beta, H alpha, means the color of this H alpha is red only, red in color. So it is red, it corresponds to the wavelength of red color of this visible light, this H alpha of hydrogen atom. Okay, and remember, from this figure you can clearly understand that as a wavelength decreases, the lines are becoming very close and close. See here, wavelength 6563 angstrom, the spectral line was H alpha here, and the wavelength here it is 4861 angstrom. See, it is very away, and between these all are nothing but something of this, they are in 4000s only. So here the value is gone decreasing also. As a value decreases, line become closer and closer. As a wavelength decreases, lines become closer and closer. Intensity also becomes less. Intensity becomes less here. Then Balmer showed one empirical formula for calculated wavelengths in case of hydrogen spectrum. So that empirical formula is given by 1 by lambda is equal to R into, so all these wavelengths corresponding to H alpha, H beta, H gamma, H delta of Balmer series was found by the person Balmer with one simple formula, an experimental empirical formula, that is 1 by lambda equal to R into 1 by 2 square minus 1 by n square. 1 by 2 square minus 1 by n square, where lambda is called wavelength. Where lambda is called wavelength and where r is called wavelength corresponding to the spectral lines, wavelength of the spectral line. In detail, if you want to write, wavelength of the spectral line. Spectral lines. Here corresponding to first, if you take, it is wavelength of one first respective spectral line. So r is Rydberg constant. It's called Rydberg constant. And where n is called the, you can take orbit numbers. So for Balmer series, the choice of orbit number will come 3, 4, 5, 6 like that, so on. And the value of Rydberg constant found to be, the value of Rydberg constant found to be r is equal to 1.097 into 10 raised to 7 per meter. So this is the value of Rydberg constant. And this is the Balmer's empirical formula for the calculation of wavelength of the spectral line of hydrogen atom. Listen here. Balmer observed that 4 spectral lines H alpha, and that whatever the wavelength we calculated for H alpha is 6563 angstrom. You can get this value with the help of very simple formula, this one, by substituting n is equal to 3. For H alpha, n is equal to 3. If you substitute 1 by lambda equal to r into 1 by 2 square minus 1 by 3 square, so because n is equal to 3, and remember, very simple here, H alpha is nothing but a Balmer series of hydrogen atom, and this spectral series corresponds to red region of visible region, and this visible region is due to transition of electron from third to second. Transition of electron from third to second. It means n is equal to 3 to n is equal to 2. Electron will transit during that it emits this H alpha. That is the meaning here. So this is nothing but what? And you will get this value if you did this. And similarly, for H beta, n is equal to 4. For H gamma, n is equal to 5. For H delta, n is equal to 6. 6 to 2. Transition from 3 to 2, H alpha. Transition of atom or atoms from 4th to 2, H beta. 5th to 2, H gamma. 6th to 2, H delta. So this is the thing. So next, after the Balmer's observation about the spectrum of hydrogen atom, then later some other scientist by name, other physicist by name Lyman, Paschen, Brackett and Pfund, they have also observed the spectrum of certain series of spectrum of hydrogen atom, and they also calculated the empirical formula for the other observed spectral lines of hydrogen atom, and we have Lyman series. So Lyman series, so I told you that. So Lyman series has got an empirical formula 1 by lambda equal to r into 1 by 1 square minus 1 by n square. In this case, n should be taken from 2, 3, 4 and etc. Lyman also observed that the spectrum of hydrogen atom in ultraviolet region, this is very important. He observed in UV region of electromagnetic spectrum. Then next is Paschen series, and this series is due to transition of electrons from higher orbit to third orbit we tell, that is from higher orbit to, that is 3, either 4th to 3, like that. And this Passion series is observed in near infrared region. After Passion, that is bracket series, and bracket series also has got a empirical formula 1 by lambda is equal to 1 by 4 square minus 1 by n square. And the last series of hydrogen atom, that is P fund series, and this will be 1 by lambda is equal to r into 1 by 5 square minus 1 by n square. Here choice of n will from 4, 5, 6 like that. Here choice of n will be from 5, 6, 7 like that. Here it is 6, 7, 8 like this. So this is about the spectral series of hydrogen atom observed by the person Balmer, Lyman, Passion. Actually Lyman is the first ultraviolet region, then second one will be Balmer series. Second one is Balmer series in visible region. This is in ultraviolet, and this Passion, bracket and P fund are in infrared region, near infrared, mid infrared, far infrared region of electromagnetic spectrum. So like this we have a study of spectral series of hydrogen atom. So in our next class we shall see about further details of this atomic spectrum and Bohr's atomic model. Okay, thank you.